Okay, so this is an example of the example problem videos that are embedded into the digital textbook for ECET 376. So with every one of the chapter examples, you're going to find one of these video solutions hyperlinked to so that you can see what the solution method that I use is to solve the problem. Should give you lots of good examples to use in the class. So this links to example 0.2.1. It's the first and only example video in chapter 0, and it basically just builds on some prerequisite knowledge that you would have learned in earlier AC or power courses. So we'll always start these video examples by restating the question exactly as it appears in the textbook. In this case, the question statement was a 90 ohm resistor, a 32 millihenry inductor, and a 5 microfarad capacitor are connected in series across a sinusoidal voltage source. The voltage source is Vs of t equals 750 cosine of 5000 t plus 30 degrees volts. Calculate the steady state current supplied by Vs of t. So the method we're going to use is called given find solution answer, GFSA, and that's a method that I'll use in all of the videos, and it's also the method that I suggest you use when attempting either the example problems or the skill builder problems, the homework problems, any of the work that you do in this class. I suggest this. So the first part of that is to write down the givens. This is just the point in which we extract the important information from the problem statement. So for example, R equals 90 ohms. That's the resistance of the resistor. Next we have L equals 32 millihenries. So we want to write that down. Next we've got the capacitance. So the symbol for capacitance is C equals 5 microfarad. So some of this is prerequisite knowledge, R, L, and C, for example, being the symbols used for the passive devices. So now what we're given is with the voltage source information. So we want to write that down. Vs of t, the voltage source we see, is connected in a series circuit, RLC. So often in the problem statement we'll actually draw it, because that's the way electrical engineers tend to communicate, is with a circuit. So we've got that Vs of t that we've drawn down there, and then we want to extract what that value is. We were given a time domain expression for voltage 750 cosine of omega t plus phi, and that form is 5000 t plus 30 degrees. So if you're unfamiliar with that, I encourage you to go look back at your ECET 277 information. So that's Vp times the cosine of omega t plus phi is a standard format for a time varying voltage waveform. So what we've done here is we've just summarized all the givens and we've drawn a little circuit schematic. Next is to write down the finds. What is it that the problem is asking us to solve for? So verbally we were asked to solve for steady state current. Steady state current is a time domain expression, so we write that as I sub s of t, where the s I'm just using to indicate supply. The next step is the solution. This is where we solve the problem. So this is the application of the principles that we develop throughout the chapters. So in this is all review. I'm not going to give you any instruction on RLC series circuit solving in the time or frequency domain. You should already know that. But generally, this is where you'll apply the techniques that were introduced to you throughout the course of the chapter via your reading. So if you are viewing a video and you don't understand where the solution method came from, you get that from the reading. So in this step, what we're going to be doing is solving a series RLC circuit. You should know that the first step to that is to convert from time domain into frequency domain by converting the passive device elements from resistance, inductance, and capacitance over into impedances. You do that based on angular frequency, which in this case comes from the time domain voltage expression omega, Greek letter omega, looks a little bit like a W, and that's 5000 radians per second. So we do a frequency transformation on all the passive components. The impedance of a resistor is just 90 ohms because it is not frequency dependent, so it's the same in the frequency domain as it is in the time domain. No math needed. For the inductor, however, we have a formula. It is J, the imaginary number, times the angular frequency times L. J 1500 radians per second times 32 millihenries. Milli is e to the minus 3. So J times omega times L gives you the inductive reactance, and for this problem that's 160 ohms. Capacitive reactance is similar. 1 over J omega C is equal to 1 over J times 5000 rads per second times the capacitance of the capacitor in microfarads. which was 5e to the minus 6 farads, minus 6 being micro. And so that gives us a calculated value of capacitive impedance of minus J40. The minus J just coming from the fact that the J was in the denominator of that fraction. So now we've got all of those values. We then need to transform the voltage from time domain to frequency domain. We do that just by writing it in its phasor version, peak at an angle of offset. So 750 angle 30 degrees, which is just taken straight from the time domain expression for the voltage. So we've done all the time domain to phasor domain transforms. So now what we need to do is just redraw the circuit in the phasor domain. We replace the time domain voltage source with its phasor equivalent and all the passives with their impedances. So 90 ohms, J160 as we calculated, and then minus J40 for the capacitor. So that is what is considered the frequency domain transfer of the time domain circuit. So it looks pretty similar. We've just replaced everything basically with phasors and impedances instead of time domain expressions and resistance, capacitance, and inductance. So pretty straightforward operation there. Now we've got an RLC circuit that we have to analyze in the phasor domain. We need to determine the total impedance. That's always the approach. When the circuit is in series, we do that via direct addition, so we just need to add the elements together. 90 ohms plus J160 ohms minus J40 ohms, just combine those using the rules for complex math. You get 90 plus J120 ohms for the total circuit impedance ZT. So next we need to calculate the current, the time domain, and to do that what we're going to do is a division. It tends to help if the impedance is in polar form, so you can do that by throwing it into your calculator. I got 150 at angle 53.13 degrees for Z of t in polar form. So 90 plus J120 in Cartesian or rectangular is the same as 150 angle 53.13 in polar. So the reason we do that is because what we want to do is we want to solve for I of t, or the phasor domain I, but just by dividing total voltage by total current, as I'm showing in this circuit model. So we just take Vs divided by Zt, and so throw those numbers in there. I'm using polar form here, so 750 angle 30 divided by 150 angle 53.13. Do that because division is easiest in polar form. So that gives us an answer of 5 at angle negative 23.13 degrees amps. It's just 750 divided by 150 is 5, and 30 minus 53.13 is negative 23.13 degrees. So that's the final answer in phasor form. We're now converting it over into time domain because that's what was asked for. So we take the magnitude. In this case I calculated the peak, so we know that the formula for a current waveform is I peak times the cosine of omega t plus or minus phi. So we just fill those in. So Is of t is equal to 5 cosine of 5,000 t. So that is the solution and the general method you'll be using in this class.